Welcome to day 2 of Zero to Hero in Assembly Language, the language of Cyber Defender by Cybervidyapeeth Foundation and CERT-In, the Computer Emergency Response Team of India. Today, we'll be looking at the first assembly program of our lives. We'll also be diving deep into the differences between a program created on the Linux platform using pure assembly and the C programming language. So let us go back to our day 2 PPT right here. And again, I'm not going into memory models right now. Let me first skip all this and directly jump to my first instruction of the day. So this is the first, technically speaking, instruction that I'm going to be teaching you. I've told you about this already. It's called the NOP instruction or the no operation instruction. It's a very simple instruction. It does nothing. No register, no values, no nothing. Just there to pad align bytes or just to delay time of the system. Attackers use it to make simple exploits more reliable. Now, how do attackers use it to make simple exploits more reliable? I will come to that. Don't worry. Even malware uses NOP a lot actually. And you can use NOP to crash other people's software when you're reverse engineering. NOP is a very helpful assembly x86 64 instruction, and we will really see its power towards day 4 when I'll give you a small reverse engineering demo. So a NOP must not access memory, as that could cause memory fault or page fault. So a NOP instruction is simply not allowed to do anything. It does literally nothing. It cannot touch memory also. The 1 byte NOP instruction is an alias mnemonic for the XCHG EAX instruction. So SCHG is basically take a value from something and copy it to something. And you can see that if you're copying something from EAX to EAX or transferring something to EAX to EAX, it is basically a null instruction. How can you take something from something and then put it in the same place? You can either pick it up and put it back, but computers don't technically have that concept of picking something up. So this results in basically nothing actually executing. Okay. So yeah, moving on. Now we understand the NOP instruction, which is roughly 6% of all assembly instructions used all around the world in every programming language and every machine code ever written, roughly. So this means that you already know 6% of all code ever written all around the world. How fantastic is that? Day 2 of learning a new thing, and you suddenly know every code ever written in the world. 6%. You already understand 6% of what every code ever written by human beings is built of. Just let that sink in for a second. Now, before we go further, I want to talk a little bit about the stack, which is a section in the memory which is based on the last in first count, or the LIFO data structure, where data is pushed on the top of the stack and popped off the stack. The stack is conceptual way of main memory, or RAM, random access memory, which is designated by the OS when the program is started. Different OSs started differently at different addresses by their own convention, or if they're using an address space layout randomization, which is a security technology called ASLR. There are other security measures built into the Linux kernels. There's also the LSM, which is Linux security modules. Again, all that is a little bit advanced for this class right now, so let's not go too deep into what a stack is. Stack is basically this, just putting things on top of each other. Think of it like that. When you push something on a stack, you put it on top of the stack. When you pop something, you pop it on top of the stack. By convention, the stack grows towards the lower memory addresses. Adding something to the stack means the top of the stack is now at a lower memory address. Okay, so let me explain it to you this way. Here is a simple image created by our visual experts. Here you will see there is high address, there is low address. In between there is stack, heap, your code being stored in RAM, and some global data that can be accessed by everyone. So the memory actually goes like this. Uh, you know, the stack grows downwards, meaning it starts at the top at a higher memory, and then it grows downward. So you can see some empty space just below the orange stack here, right? that is where it actually grows. It grows downwards. So it grows towards lower memory addresses or lower hexadecimal numbers. Addresses are what? Hexadecimal numbers, right? So addresses in memory are hexadecimal numbers, which can also be represented as binary numbers or even decimal numbers if you wish to do so. So because these hexadecimal numbers are there, when your stack grows, it grows downwards. When your code or heap grows, it grows upwards to fill this empty space right here. Okay. Now you can also see that bottom is the lower number, lower addresses. So lower values in the hexadecimal and higher addresses are on the top. Again, if this is a little bit confusing right now, what does grows means? Grows means the more data you put in the stack, the more stack starts to swell up from the bottom. Same way, the more heap, the more code, the more global data, the more read-only data or whatever, the bottom part grows upwards to fill up the empty space. That's all you want to understand right now. Okay. So the RSP, or the really long stack pointer, points to the top of the stack, the lowest address which is being used. While the data will exist beyond the top of the stack, it is considered undefined. So this is an interesting concept, but I'm actually not going to touch RSP yet. I'll wait. So the stack, the next slide on the stack here talks about what can you find on the stack and some other information that is available. So things like, return addresses to a function. So say you have an int function, your function returns an integer, right? So the integer that is returned by your function, your method, your subroutine, that is usually stored on the stack. Your local variables, sometimes the arguments that are being passed between functions. Please note the italics case of sometimes is intentional, sometimes really does mean sometimes. Save space for registers so that functions can share registers without smashing the value for each other. So this is important. You want to make sure that registers are empty for the most important data, because registers are the closest to the CPU and are also the fastest form of memory available. So RAM becomes kind of like a secondary storage, and you give priority to the registers and to the cache in modern CPUs. Okay, cache and registers are usually what takes priority over RAM, and then RAM comes into the job. And if RAM also fails, then you have ZRAM and Linux swap in the Linux and BSD world, which allows you to have some kind of tertiary memory on your hard disk or your SSD. Okay. So here's a simple stack diagram, and this is a beautiful diagram. Kudos to again Cybervidyapeeth team. And I just want you to look at the diagram for a few seconds to understand what is going on. What we have done is zoomed inside the stack inside a RAM and showed you a simple C program and how it will connect inside or how it will be placed inside a stack inside the RAM chip. So here you will see that stdio data include int bar int y. So it takes a parameter int y, the function bar. We have int a equals 3 into y. Okay, so whatever is passed will be multiplied by 3 and then put inside a. Then we can see, bar returned d, percentage d, and then we supply the value of a on the printf. There's way too many exploits I can think just for this program. In no way this is a safe program to deploy in a production environment. Printf itself has been known to be very unsafe. Just for learning purposes, we are looking at this. So you see how it works is that the main function is at the top of the stack and hence at the highest memory address for your program. I repeat, for your program. Below that comes foo and below that comes bar, and each function is getting a frame in the stack. Now frame can be thought of as a region inside the stack region that is dedicated to be used by your function. It is usually defined by the compiler or in some cases the assembler, and if it is happening by the assembler, it is usually defined by you because you are the assembly language programmer. If the compiler handles it like GCC for example or LLVM, then definitely what's going to happen is that the compiler is going to take care of the size of these frames. So a lot of people get confused. A lot of people ask me when they're dealing with this simple stack diagram that sir, I don't understand really why, what is this stack top, stack bottom, how memory addresses are going up and down. We will have a short exercise on day 3, and that exercise is going to jog you up and get you up and running. And it's a very simple exercise, but it's what that helped me, like 7-8 years ago when I learned assembly first. That was the exercise that helped me grasp how to navigate the stack. So I think that exercise is really helpful, and watch out for day 3 where we'll be going into the exercise. So now let's talk about our next instruction a little bit, which is the push or the pop instruction. So two instructions side by side we're looking at. First we have the push instruction. The push instruction is a chord word. I'm not going to explain what a chord word is. Please see previous day to understand that. Onto the stack. The push instruction automatically decrements the stack pointer RSP by 8. So now this is interesting, and I think there's going to be a diagram right here. There you go. So here you see that there is a simple instruction push RAX being executed, and this is a simple diagram that demonstrates push RAX. Here we see that this is how the registers and the memory inside the stack looks, okay, on the left side, beforehand and after the execution of the command push RAX, or the instruction I should say. This is how it looks. So let's try to understand what's going on. The RSP or the stack pointer points at this address. So here there is a fault. The fault is very simple actually. The fault is that the RSP, okay, no, actually this is correct only. Yes, this is correct only. But this is not how it will look. See, I'll tell you. The RSP or the stack pointer always points to the last memory address where there is data, right? If you go back a little bit, you will see the RSP or the really long stack pointer points to the top of the stack, the lowest address which is being used, lowest address which is being used. So here you can see the address is decrementing, right, from top to bottom. Is this the lowest address with the data, or is there something below it? There is something below it, meaning that our visual artists have made a tiny mistake here. RSP should be actually pointing at 14FE08. It should not be pointing at 14FE10. That is wrong. RSP actually points to 14FE08. Now imagine that our RSP points here, meaning that this is the last place in the stack where there is some data being stored. Okay. Just below this, all the data is considered undefined. Okay. So by undefined, what it means is that there is some data, but we don't consider it as being there. Okay. For example, once one day there was some data 3 here. We deleted 3 in our code. So technically 3 still exists here. It's just that the stack pointer went from 14FE00 to 14FE08. That's basically what happened. To give you a glimpse of what I'm talking about, this is a formal way of saying it, that while data will exist at addresses beyond the top of the stack, it is considered undefined. Okay. Again, don't worry about the RMX addressing format. We will come to that in just a second. So here you should be able to see some interesting things. The first thing I want to note is that RAX has a value of 3. It stores the number 3, basically 00000000003. And RSP has 14FE08. So you can actually see that RSP points to 14FE08, but by mistake we have pointed it to 14FE010. Computer will not make this mistake, okay? This is a human error. Don't worry. Computer will always point RSP to 14FE08 if it is 14FE08. Now, when you run the command push RAX or the instruction push RAX, what happens? What happens is that the RSP is decreased by the number of bytes required to an address where there is ample space to accommodate this number 3. And the RSP is updated. So you can see the RSP now has 14FE00, 14FE00, which is the next memory address. Okay. And you can also see that the memory address was, technically speaking, decremented by 8. Now, why was it specifically decremented by 8? is another homework question that I want as an answer in comments. So this is the push instruction, very simple. It pushes something on the stack as the stack grows towards the lower memory addresses. The another instruction is pop, which is opposite of push. It removes something from the stack. Here is an example of how the pop instruction works. You have registers before, so RAX having 3 and RSP having 14 FE08. Okay. No, I'm pretty sure this image is wrong. This image is definitely wrong. RSP should not be pointing at this number. RSP should now be pointing at 14 FE00. I apologize for the wrong marking. The RSP or the really long stack pointer should point at 14 FE00. Okay. So pointing at 3 because this is the last value, and anything below that is considered undefined. When we run pop RAX, what happens is that the value stored in RAX, which is 3, that is popped or removed from the memory. So here you can see that we have actually removed, and now 14 FE00 does not have our value 3 anymore, and our RSP has been incremented by 8. So last time I said it was decremented by 8, and now I am saying that it is incremented by 8. Don't worry, I'll correct the diagrams, and in the next class you'll see the correct diagrams also, and I'll take 10 minutes to explain those diagrams again. But I think you should be able to imagine this much, that RSP is pointing at 14 FE00, and when we pop it, it removes the value, so the RSP goes up by 8. Simple, very simple, right? Please note that the value 3 that was stored here at 14 FE00 has not disappeared. It is still in the memory. If we do digital forensics, we can still find it. It is still there. It is just that we are considering it undefined. Data written in memory does not just magically go poof. Okay, it is still there, and this is actually the basis of a lot of memory forensics, advanced memory forensics. So data is still stored. A lot of people think it's not stored. When you do a pop instruction, the data is removed. It is not removed. That is wrong language. It is simply considered undefined. It is still there. The data is still there. Remember that. That's very important to know as hackers. To understand some basic stuff about 32-bit, okay, if you are executing this in 32-bit, values will be removed with 32 bits instead of 64 bits. Okay, I won't say anything more than this because this has a hint to why 8, increment and decrement by 8. This already has a hint, so I'm not going to give you too much about that. Okay, so now you know 3 instructions, which is 5%, and you have 10%, so roughly more than 20%. I think you guys know. Yeah, that's true. More than 20% of every code ever written in the whole wide world is now known by every single one of you students. Just let that sink in. So easily you have learnt every single code ever written, more than 20% of it, in 2 days. That is the beauty of assembly. Everything is assembly. Down the lane, at the lower level, everything can be decompiled and disassembled, and you can have a look at the assembly language code, which is fantastic. Now here we are talking about subroutine, which is our next topic. So let's go back. Let's not dive into that, and I am going to go a little bit into the RMX addressing forms. So what is RMX? So RMX is a well researched kind of addressing form. You can think of this as a made up term. Okay, this was made up by Xenon, who's a cybersecurity researcher, and here you can actually see how the RMX addressing form works. Say we are pushing an RM16 this is valid in 64 bit mode, but in compact LED mode this is also valid. So you know what, I'm not going to explain this diagram actually has some very interesting things like leg mode and compact mode, and has actually very ample description as well about what's going on. So what I want you all to do is to try to understand this diagram, to pause, just read this diagram 4, 5, 7 times. See, assembly requires a lot of patience. It's okay if you don't understand every single thing. Even I didn't when I start. So you must take your time, build your knowledge bit by bit. So to understand very simply, in the Intel syntax, how it looks like the RMX form. A register is simply written like RBX. If you want to know the location of the memory of the value stored in RBX, so for example, RBX has the value 3 inside of it. If you want to know what is stored at 3 and not get the value 3, then you use these brackets. Brackets will take you to the memory address of 3. If you want to make it more complex, you can do something like RBX plus RCX into X. Here X has to be 1, 2, 4 or 8. So you need to multiply it by 1, 2, 4 or 8. This is defined in the Intel manual since 2012. So you need to, fixedly use these values for X. So you can, control your jump in memory. So remember I told you when you put these big brackets, you can actually go into a memory address. So here, whatever is the solution of RCX into X plus RBX, that number, say that number is 21. 21 is actually going to be the memory address from where the value is picked and shown to you or used by you in your program. Okay. You won't use the word, the number 21 or the memory address 21H, H as in hexadecimal. Instead, 21H is basically the location at which their value will be picked up. Now 21H can have any value. 21H can have 500 also. 500H. That is the value that will actually be used. So please do not get confused. When you use brackets, you are actually going to the memory address and picking the data rather than using the memory address itself. Here you can see that we can also have a slightly more complex way of navigating the memory. So here we have uh, memory base plus, inside memory we have base plus index into scale plus something called as displacement. Now this is a little bit into mathematics territory here, so I won't be going too deep into okay, what is an index, what is a scale, and what is displacement, and how do we define displacement here. Just know that this is a very interesting way to jump around in memory. Okay, you can actually control your jumps. You can multiply by something, add by something, and then add something even more to that result to reach your specified result. That's all I want you to learn from this right now. If you want to understand where all this is used, here's some example. Here you can see that base plus index into scale plus displacement has natural applicability to multi-dimensional array indexing and arrays of structure. It is used by Python, for example, at a very low level. Python uses this technique to index its lists. So when I say that future instructions support access to memory, I mean that memory is encoded in the RMX form. Okay. And when I say that RMX, I mean that something that could be as simple as a single register or as complicated as a memory address calculation in that form. Before we go any further, here is a super simple example of two types of push that we can do. We have the push register, which basically just pushes the value that is stored inside that register. So for example, 3 onto the stack as we saw in the diagram, or push memory, which actually goes to the 3 in the RAM, the position 3 in the RAM, the address 3 in the RAM, picks the data, say 500, and then uses that in your code or pushes that to your stack, because here we are pushing it to the stack. Okay. So push RBX is an example, push RBX plus RCX into 4 is an example, and push RBX plus RCX into 8 plus 20H is another slightly more complex example of memory navigation. So now let's go towards the beginning of this PPT and talk about memory models. So the question is, what is a memory model, right? So to understand a memory model, let's talk about the 8080 Intel CPU. So the 8080 was most frequently used with the operating system CPM80, being at the top of the installed memory made of CPM80 a little unusual. Sometimes this was done so that it could be contained in a ROM, but more often it was done to get it out of the way and provide a consistent memory starting point from transient programmers, which unlike the operating system were loaded into memory and only executed when necessary. So this is some history right here. This is very interesting history, by the way. I'm a complete geek for cool computer history, as you can clearly see from the amount of interest I have. But not to waste your time and my time, this is going to be here on your screen. If you want, you can read further about it. To get a small look at the memory model of the 8080, here's an example. This is basically the memory model. The transient program code used to be stored here. There used to be some unused memory here. Then there used to be the operating system being loaded into the RAM. Then there used to be addresses without installed memory. Okay, this used to be the top of the installed memory, and this used to be the bottom of the installed memory. Memory used to be around 16 to 32K in back in those days. Okay, and this was a 16-bit CPU. So the era was of 8-bit, 16-bit kind of a world. So most corporate programs are also either 16-bit or 8-bit. Some cutting edge stuff was being written in 32-bit, but 32-bit was not widely available. Only like some researchers had access to 32-bit, so it was extremely hard for a person to get their hands on 32-bit during this era. The 8086 model inside an 8086 memory model. So here's a very simple example of taking the 8080 model and putting it inside the 8086 model. Okay. Now here you will see that we have a very interesting memory model. We have a 20-bit memory address bus. We have a 0FFFH. You have some unused memory. Then we have 080000H and 00000H. So here we can see that the 8080 memory model is inside a 8086 memory model. So we have encapsulated it to be operatable by a 16-bit 8086 processor, which is again an infamous CPU created by Intel. Okay, it's very popular. Another thing to note is that there are 20 address lines and 1 MB of memory available on the 8086 and the 8088 CPUs. 4 gigabytes of memory could be addressed by the 386 and later Intel CPUs without being divided into smaller chunks. So 4 gigabytes of information could be properly processed, right? Back in that day. A segment is 4 gigabytes when a 32-bit CPU is running in protected mode flat model. So one segment is typically sufficient. It was necessary to deal with a massive amount of DOS software that was still in use and was written to use segments. Therefore, later CPUs were given the authority to restrict themselves to what 8086 and 8088 could address and execute in order to ensure backwards compatibility. A clever method is used by the Pentium class CPUs to temporarily transform themselves into an 8086 when they need to run software created for real mode segmented model. This is known as a virtual 86 mode. It is offered great DOS program backward compatibility. It is still available in many modern CPUs and many corporate CPUs and server CPUs. This feature is actually still provided by Intel. In case say you have a fantastic software written back in the DOS days, maybe in the COBOL language or in DOS, written for DOS, and you want to use that program even now. So say you're a bank, okay, you have no choice but to use it. What will you do then? It's a critical piece that makes you money. It's a very optimized program also. It runs fast, everything is there. You don't want to pay somebody to remake the program, and in the long run it's working fine. So this is still a feature a lot of you might not believe, but Intel still offers MS-DOS compatibility support through this technique. Any an x86 CPU can see a full megabyte in memory in real mode segmented model. Now you might be asking me, okay, what is all this? What are you what jargon is this? Protected mode flat model, real mode segmented model. Take a deep breath. I'm coming to it. I told you it takes time in assembly. Pieces take some time to fall in the right place. In other words, the CPU chips configure themselves so that they may pass a 20-bit address to the memory system using 20 of their 32 address pins. Although those CPUs are capable of seeing a full megabyte in memory, they're limited to viewing it through 16-bit blinders, meaning that even though a CPU might be able to see 20 bits at a time or 20-bit addresses at a time, they could only technically use 16. They were limited by the hardware and the thing at the time. There's also loading megabyte through 64,000 blinders. So this is the same thing. We just increase the number of bytes here. There's also collective terms of memory. So as you can see, these are the terms that I've already discussed. There's the paragraph boundary with a memory address that is equally divided by 16 characters. So you have byte with a value of 1 in decimal and 0 1 hexadecimal, or H as we put after the hexadecimal numbers. Usually a small h or a capital H is considered compulsory, okay, when you're writing a hexadecimal number, because other than that, it's really hard to tell the difference between hexadecimal number and a real number. It can get out of hand very quickly. So here we can see that word is basically 2 in decimal or 02, double word is 4, a quad word is 8, 10 bytes is 10 or 0 AH in hexadecimal. A paragraph is considered 16, a page is considered 256 or 100H, and a segment is considered 65,536. Okay. So again, segments and offsets, slightly more concept, advanced concept, not going into this right now. We'll come back to this diagram. Actually, this is a fantastic diagram. I really want to explain this right now, but I'm not going to. I'm going to pause here for a few seconds. So if you wish to pause the video and just go through this, the text and the diagram, be my guest. But I'm not going to this right now. See, in assembly, I gotta tempt you. It's the greatest. It's the most interesting topic in the world of computers. The most fascinating black box magic. To understand it, you need to take it slow. Understand bits by bits by bits by bits, and then suddenly you'll have a eureka moment. So here's some information about 16-bit and 32-bit registers. Again, this is more or less historical and some housekeeping information. Nothing very extraordinary that will help you when you're coding. But definitely pause and read through this as well. Again, I'm not going to read all this information. I've typed it out for you so that you can pause the video and go through this information. Reading it once or twice should be good enough. There are some general purpose registers when you're talking about Intel or AMD CPUs, and these general purpose registers basically help assembly language writers to store a lot of memory while coding programs. Okay, and they are used for a lot of different kind of activities. Like you can put coordinates, you can put offsets, you can put return values, anything you want, honestly. Okay. The general purpose registers are basically memory locations found inside the CPU chip itself. This is one of the reasons registers are extremely fast. Registers are on the CPU chip, also known as a die nowadays, a CPU die itself. Okay, and they all have names rather than numeric addresses. So they are special in nature. Okay, everything else in the world inside computers has a numeric address except CPU registers, especially the general purpose ones. They have a name. Okay, REX, RBX, AX, BX, CX, DX, like this. They have name. The general purpose registers in our modern 32-bit world can be divided into three categories: 16-bit general purpose, 32-bit extended, and 8-bit register halves. There's also a really long extended 64-bit registers now. Okay, so RAX, RBX, RCX, RDX, RBP, RSI, RDI, RSP, etc. If you put R in front of it, it's for 64-bit. If you put E in front of it, it is for 32-bit. If you remove both R and E from in front of it, it becomes 16-bit. If you remove that also, it becomes 8-bit. Okay. So in reality, the 32-bit registers, 16-bit and 8 bits are just certain names for certain regions. By expanding registers from prior CPUs, the x86 CPU family has been able to expand its register set. This is true, and I've showed you a diagram. If you go back to day one, you'll see a diagram where I'm showing you different registers: R0, R1, R2, RDX, RAX, like so. And you will see that how I'm showing you 64-bit, how I'm showing you 32-bit, how I'm showing you 16-bit, and then I'm halving the 16-bit to show you 8-bit lower and higher range of memory location. The 32-bit architecture naming scheme for EAX, EBX, ESI, EDI, etc., came somewhere around 1986 to 1988. So now let's go a little bit ahead and have a look at subroutines. So what is a subroutine? So subroutine can be thought of as, for the time being, a reusable block of code. Okay, this is what you would usually call a function inside the C programming language. Of course, there are other types of subroutines. There can be cases, special cases. There's always exceptions here, but usually a subroutine is basically just a reusable block of code, which is literally the definition of functions in basic programming theory, and that is how it's been implemented in the C programming language. So now the question comes to, okay, how does it look in, when compiled, after compile time? So here's a simple example in front of you. Int function return 0x beef. Okay, by the way, that's not beef, that's actually a hexadecimal number. Uh, you know, you see what I did there? That is a hexadecimal number, okay? Just to be very clear with all of you. Int main function, so we call the function and then we return food. Okay, again, this is F00D. It's a hexadecimal number, just to be very clear with you. And a lot of people ask this, so I'm going to actually switch to a IDE here called Code Blocks. It's a simple IDE that lets you develop for C, C++, some basic applications and Windows specific coding. In here, I want to ask you this. When we look at a program such as this, with include stdio.h, include stdlib.h, int main print hello world return 0, and I build and run this program and we get hello world as an output. Here's my question to you. We return the value 0, right? The process returns 0 because the return value is 0. So this return value here, is it a decimal, a binary, a hexadecimal, a octal, or none of these? Is it something else entirely? Is it a special code? What is it? And I can see a lot of you, thinking and guessing here. What exactly is this 0 here? And can I just say something like 1 here? Does that work? Can I just save this file and compile and run, and will the process return a 1 to me? Which means error, right? Let's see. Let's zoom in and see. Process returned 1. But our code got executed just as, it was supposed to be. That's weird, right? What if I return 9999? Does that work? Does any decimal number work? What's going on? Let's compile and run that again, and let's have a look at this C program running and launching. So just give it a few seconds, and yes, it seems to run. And sadly, the answer is literally on the right side of this number. As you can see, it's been written as a hexadecimal number here. So what happens in the return is that all the values that are being returned are actually hexadecimal values. So I can do something along the lines of this, and this is going to work because, yeah, there we go. See, because return returns hexadecimal values. Now again, this is on a higher level. At the lower level, it's all binary patterns. Okay, you know, when you're really talking about how Windows operating system or how Linux operating system or how BSD, Solaris, any derivative of Unix, or any other, new programming language, maybe made in Rust or Golang or whatever, handles it. At the lowest level, they, probably deal with it in the binary pattern segment. So they can convert any number into binary, octets, and then they handle it that way. But here at the higher level, when you're dealing with software or on a slightly higher level, you realize that everything is being handled in hexadecimal, and that is actually very much true. And the reason is because hexadecimal can be used as a shorthand for binary language. And the reason is because binary is, very cumbersome to write. Writing something like 0010000001000 is much harder, and you can just say something like 14FH, and it's much easier. So what you need to realize and understand is that hexadecimal usually reduces the amount of quote unquote space you need to represent a number, thereby allowing you to write bigger numbers with lesser digits. And that is exactly what is happening here. You can see that 0xb is a hexadecimal number, which is actually 48879 in decimal, and that is the code that was returned by our program. Please note, changing the return value seems to have absolutely no effect in the execution of our program. Now, what I'm going to do is, I know for a fact where this file is stored. So I am going to go and open up IDA64. So for those who don't know what IDA64 is, IDA64 is a fantastic and possibly the world's best decompiler and disassembler, as well as reverse engineering and malware analysis tool in the world. I'm using IDA Pro. It's a purchased copy of IDA Pro. So I am going to select new here inside the IDA's quick start menu, which is the first thing you see when you start up IDA Pro. This is paid software. There is a free version. So if you wish to download the free version and try to follow me, you won't see all the features, but the basics will still work. Okay, so you can download the free version on the Hexray site, and then you can actually follow through to what I'm showing you here. So I want to show you the disassembly for this code right here. So for that, what I'm going to do is I'm going to type new. Now what I'm going to do is I am going to select the file, and I know the file is in documents, binaries, subroutine binaries, binaries, debugging binaries, and subroutines.exe. So I'm just going to select that, and I'm going to select portable and executable for AMD64 PE. Now what is PE? We will be going into that. PE is a whole other world of its own. It is a very important and interesting topic for anyone trying to understand a Windows assembly language. So we'll go into that in just a bit. I'm going to load the resources, and I'm not going to change anything else. I'm just going to click OK. And yes, I am going to make sure all this is there. Cool. So dwarf debug information is there. Do you want to import it? Yes, I do. There we go. So the initial auto analysis is complete. So if you see down here, the initial auto analysis has been finished in the output. So that means that our binary has now been analyzed. Now this is a very small binary, so I didn't expect it to take more than a few seconds. So yes, that is true. And here is the interface of IDA Pro. And here's the fun part, right? Here you can see there is a graph here, which is called the view A right here. You can see there are multiple tabbed views here that you can switch between. Now, IDA Pro is not the focus of this course, I know, and it's a very heavy software. It takes decades for people to learn this software. It has like so many features, and it's basically the industry standard. What I'm trying to show you here is the disassembly of the program we just coded in. So this program doesn't have like too many logics, right? Because of that, it literally has only this much code inside its main function. You can see here int cdec1 main. And by the way, those who don't understand what this double underscore cdec1 main is, for them, here's my recommendation. Google it. When you Google it, you will find references to it. For example, you will find C++ forum reference, which will talk about what exactly is this cdecl is it. The cdec1 or L portion is the calling convention, and you can actually click here and further research what it means. Stands for C declaration, is a calling convention for C programming language and is used by many C compilers for the x86 architecture. The subroutine arguments are passed on the stack, integer values and memory addresses are returned to the EX register, floating point values in the ST0, x87 registers in the EAX, ECX, EDX are caller saved, and the rest are callee saved. So caller saved, callee saved we have not got into this yet, but it looks like this stands for C declaration and is a calling convention, which means C language is being used. Perfect. Exactly, what we were looking for. So let's go back to IDA. And we see some parameters being passed. I'm not going too deep into what parameters are being passed. There's some environment variables also being passed here. Inside the main function, there is a push instruction. So we have seen the push and the pop instruction right here. Okay. And by the way, usually in programming, push and pop are used together in the same program. So if you're pushing something, you'll definitely be popping it if it's a simple program. And you can see here we have done a similar thing where we have pushed RBP register, the value of RBP register, onto the stack. Okay. And then we are popping it just a few moments later. That is incredible, right? We finally understand what it means. After that, you can see the move instruction. Now, if you want to know a lot about the move instruction, all I'll just say right now is that it copies, it doesn't move. That's the first thing people get wrong. It copies, it doesn't move. So if you're a Windows user and you're used to the move option on your Windows or Mac system, also known as the cut copy paste, then or simply cut paste in modern times for all the Gen Z kids out there, then basically what's happening is that it's taking the value stored inside RSP, it's copying that value and putting that into RB. Okay, then the value inside RSP is being subtracted by 20 hexadecimal. Then a call is being initiated, okay, to main, which basically just calls a global initializer and the return statement. And let me go back. Okay, by the way, this is all housekeeping code. By housekeeping code, I mean this is code that we didn't write, right? So if I go take you back to the code here, did we even say like, yeah, reduce the stack pointer RSP by 20 hexadecimal, create space? No, nothing, right? We never said anything like that. So all this is actually happening by the compiler, right? The compiler is smart enough to do all this. And then you see here a Lee instruction. Again, I'm not going to waste too much time with the Lee instruction right now. And the Lee instruction is similar to move instruction. That's all I'll say for right now. Some of you can see a comment here in the debugging file that whatever this buffer it stores the hello world. And if you hover over it in IDA, you can actually see that it's a db value to hello world, and you are completely right. It is a db value to hello world. And what is a db value? If you remember the first assembly language program that I showed you, there also I had a string, and that string was basically some message, and that message was a label to a db value where hello world was being stored. So similarly, here in our Windows also, a similar logic is being performed. Then we do a call to putS. putS is a system call, which basically lets us print to standard output. Now the standard output in this case is our monitor, which is the screen that I'm currently sharing with you all. And then we move the value that we need to print, sorry, the value we need to return to EAX, and then we add 20 to RSP because we had subtracted before. Notice how symmetrical this program is. Okay, and then we pop RBP because we had pushed RBP, and then we run the return assembly instruction, which returns the value stored inside EAX if nothing is mentioned. So because nothing is mentioned after return, it's just going to return whatever stored inside EAX. Okay, and then we end the main. So this looks like a very complex program, but if you try note, maybe you don't understand fully what's going on. But one thing I'm sure about with all of you is that you can read this program and you can go like, okay, this is very symmetrical in nature. There are some rules here clearly, right? You can just look at this program and go like, okay, some things are being added, some things are being moved, some things are being subtracted, some things are being given a phone call, but it all looks logical somehow, right? And that is, the idea behind reverse engineering. Half the reverse engineering I learned was I taught myself through patterns, and this is a great lesson in pattern recognition. Reverse engineering is not about spending decades learning as every nook and cranny of assembly, and it will take you decades, especially with architecture as complex as x86. And then you have more like MIPS and ARM or RISC-V. You don't have time to dive deep into everything if you want to become a successful reverse engineer, exploit writer, malware analyst, any of these fields. It's gonna be really hard if you're learning assembly for cybersecurity. You have to look at it from a hacker's point of view. Is a hacker going to spend too much time understanding this? Probably no. They will just try to understand the part that is useful to their exploitation and move on. And we also need to have a similar approach. We always say, to beat a hacker, you need to think like a hacker. So that's what I'm trying to instill in you here. Just because you read something and you don't understand it doesn't mean you cannot appreciate it or even find a bug in it. When you start to understand that, you realize that, okay, I'm starting to get a hold of this. Okay. So IDA is a very complex software. As you can see on the left side, you have a function list of functions that were extracted. You also have an imports tab towards the right here about all the imports that this binary is doing. Uh, so many imports are actually happening because of the stdlib library that I've imported inside the code here. If you come here, you will see the stdlib. Stdlib actually adds a lot of unnecessary clutter to the binary. Technically, I could have removed this and it'll look just a teeny tiny bit lighter. So the program's compiled again, and I'll need to close IDA and open it up again for it to work. So I'm not gonna do that right now, but yeah, you get the rough idea. Also, please note that uh, IDA is just crazy powerful. I mean, it shows you every single part of the binary, the hexadecimal, the string formation, the binary format, everything. It can extract so much information from the binary that it's stupendous. There's another popular tool that I want to quickly show you. So let me quickly just don't pack the database, don't save the database, and hit OK. And the other tool is called Binary Ninja. Okay, there we go. So I'm going to execute Binary Ninja. There we go. And now I am just going to go ahead, click on open an existing file. And I am going to go inside documents, bins, subroutines, binary, debug binary, subroutines.exe. And we'll give it a few seconds for it to load in the binary. Perfect. Now you should be able to see it properly. So this is the interface of Binary Ninja. Now Binary Ninja is another very popular industry standard tool that has been recently getting a lot of features and attention. Here inside Binary Ninja, I've loaded the exact same binary, and I'm going to show you the power of Binary Ninja right now. Again, this is a paid version of Binary Ninja, so it may have more features than the free version or the trial if you wish to download and use that. So in here, I'm going to first of all select graph and select disassembly. Now here is the disassembly, more or less the same disassembly you just saw in IDA Pro. Okay. Now I'm going to click disassembly here and select low level IL. So IL means intermediary language. So here's another concept in assembly language and reverse engineering and understanding assembly deeper, is that intermediary language allows you to have kind of an intermediary logic between high level and low level, between say C and assembly, because converting from C to assembly is easy, but going back is really hard. So to understand and break down those logic structures in assembly, what Binary Ninja has done is introduced an IL or an intermediary language that they have created. It's a pseudo code language. So it doesn't really exist, but it helps you understand the code better. So here I'm going to select low level IL, and you will see that the code got compressed a little bit. Now you won't see a lot of the bullshit. You'll see simple code like push RBP. Okay, so we are pushing RBP. We are making RBP is equal to RSP. Then we are doing RSP equals to whatever the values of RSP is, which is basically RBP's value minus 20 in hexadecimal. Then we are calling some structure code. Then we are loading some read-only data, which is stored inside the binary, which is basically hello world. Then we are calling a system called puts. Then we are storing beef into EAX. Then we are doing RSP equals to RSP plus 20, so exact opposite of what we did here. Then we are doing RBP equals pop. This has not properly been processed by binary ninja. It should be pop bracket RBP, technically speaking. But again, this is a fake language. This is a fake format created by binary ninja or Benja to make it easier for you to understand how to disassemble pre-compiled programs. Okay, and then there is simply return jump pop. So simple logic, nothing too complex. You can see here that this is a 64-bit main function. So I'm going to go to the medium level IL and notice how suddenly the code got even shorter. Now it's looks easier, right? It looks simpler. Logic is understandable, isn't it? Let me go to high level IL. Notice that at medium level IL, you actually saw the name of the register where the value of return value was being stored. But now notice that all registers are gone and there is just a system call and a return statement, nothing else. So this pretty well summarizes the logic of the main function, doesn't it, that we have written. Let me go to pseudo C. Now there's also a pseudo C in here, so I'm going to select pseudo C and it's going to just put in those semicolons and make it look like C. And by the way, this is C code. I could literally just copy this right now and technically speaking, this will work inside a main function if I just paste it. And let me prove that to you by going here, pasting this in, removing this. Okay, now puts will directly not work because okay, it might. I have never actually tested it. It works. There we go. You know, learn something new every day. Perfect. So let me close this up. So yeah, that code that you see right here, this is basically like C now, very close to C now. It has the C syntax and everything and seems to be working in the compiler. So, you know, maybe it's 100% C compliant. Now there's no guarantee. That's one of the reasons they say pseudo C. So if it's a very complex program, there's no guarantee that the code you're seeing here is going to be like 100% copy paste and run, but it's going to be C compliant as much as possible. There's also some advanced IL forms that they've added in the the recent version, which is the lifted IL, the low level SSA form, the mapped form, the mapped SSA form, the medial level IL SSA, and the high level SSA. So this is the high level SSA. Here we are talking about the memory and the mnemonics. If you don't understand what SSA is, it's completely fine. Don't worry. Here we are dealing with some basic pointer logic. So I'm just quickly going to take you through each logic and not explain the advanced forms too much. Okay. This is the low level IL SSA form. Okay. Here we have medium level IL mapped. Here we have medium level IL mapped SSA. Again, a lot of information. And then you have SA form. Okay. There we go. So I think I've shown you guys, some of the glaring features of Benja as well, and I've showed you the code in another tool as well. On the left side here, you have a list of functions just like IDA. You also have a cross-reference function for filtering and data references, and you can actually go up and down in the binary like so. So here's some additional code that is stored in the binary. You can just do it like this. By the way, a lot of you might be thinking, okay, what are these graphs? These are code that you did not add. So remember I was talking about stdio and stdlib having some additional overhead code that you don't write but gets added to your binary. Yes, that's the code that you see in the graph right here, and some preparatory code added by the compiler actually. So let me now exit this and let's go back to our ppt. So we have actually seen the program in assembly quite well now, and we should be well versed with it. which is good news all in all. Now we have also seen the call procedure in action when we call the put s. So I'm not gonna waste too much time. Just I'll explain it to you like this, that it transfer control to a different function in such a manner that the control can later be resumed to where it left off by first pushing the address of the next instruction onto the stack for use by the return function. So whenever call happens, you have to return back to where you were called from. Okay. Now here there are two entities involved. There is the caller and callee. So if you go back here, the caller is main because it's calling function, and function is the callee. It's what's being called. Okay. And calling basically means just telling the other code to run and giving the control to the other code. And this is done through the call instruction assembly. Okay. And basically what happens is that we have to manipulate the instruction pointer or the really long instruction pointer in modern systems, RIP, in order to give the control to somebody else, right? Because RIP is the magical register which stores the the address of the next instruction to be executed. I repeat, the address to the next instruction to be executed, not the next instruction. It contains the address to the next instruction that is to be executed. Okay. Add and sub, we have seen they're very simple, just they do add and subtraction. I mean, this shouldn't be too complicated. I'll just stay on this PPT for a minute or so and then I'll move ahead. So, if you have any questions, please feel free to mention them in the chat box or in the live chat, depending upon when you're seeing this video, and I will be more than happy to answer your questions. Also, please note to like, share, and subscribe our video and channel, and make sure to spread the love and knowledge and share it to your family and friends who are interested in learning more about computers, computer security, assembly, and hacking. And we'll be more than happy to have a big family joining us and a lot of people learning from us. So feel free to join us, and please like and share the stream so that we can keep bringing this great content to you for free. So calling a subroutine, there's some important points to note. The first thing is that function is a dead code, meaning that the return value is not used for anything and the main always returns B for food. So if you look at this code here, function is dead code, and dead code logic is simple. Even though you are returning the value beef, that value is not being used in the main. Instead, main just returns food. And let me show this to you by doing the exact same thing. Let me ask you, what is the point of this code? What is the point of the function fun existing? Is it really doing anything? Because the name has been mentioned in the main, it will be executed. But the return function, is it actually doing anything with the value 14 that it is returning? Let me save and run it and let's see. And we get food as a reply. We don't get 14, we get food. But some of you a little smarter, students are gonna ask me if this will work or not. And yes, it does. It will work. Yes, you're right. And now it's not dead code. So now, if I was to delete this, the program will not compile. You will get an error which says undefined reference to fun. So now it's not dead code. It is important, it is imperative that the function fun exists. Otherwise, the main function will crash. Your program will crash. Okay. So here, this becomes a non-dead code. But if we did, what we were doing before, this is dead code. The fun function has literally zero reasons for existing. It's useless. Okay. That is all that we are trying to say here. Yes, this is also a nice point right here. If optimized, the compiler would remove the function. Yes, that is true. The fun function will be removed if you set the GCC compiler to optimize. I have not set my GCC compiler to maximum optimization, which is usually O2 optimization. So O2 is basically what Linux also uses. Usually, when you're compiling packages locally, you will use dash pipe dash o2 dash march equals native. That is usually the the flags that are used with GCC, and most compilers actually these flags exist and you prefer these flags. For those wondering what were these flags that I was talking about, I'm going to quickly write them out for you. uh, the flags are mr or architecture equals native, so that GCC can quickly identify your architecture, dash o2 and dash pipe. These are usually the ones that I recommend. There's also the so this is usually what I use to locally compile and optimize my program. So if you're into GCC and GDB and compiling stuff on Linux yourself, then this is usually what you want to use to optimize packages on your local system. You can use link time optimization, LTO, and you can make this O3 and doing like heavy optimization, but it tends to break packages. Okay, like especially when you're dealing with Slackware, Gentoo Linux, or Linux from scratch and compiling your own packages like I do. It takes time. If you, as the listener right now, don't understand any of what I'm saying, I just decided to nerd out about Linux and BSD because I'm a Linux fanboy. Okay, so forget whatever I said and let's go back to the class. And we'll come back to it when the time is right. So here we have a simple stack diagram for a very simple program. So here we see three functions: main, foo, bar. Okay, main calls foo calls bar. Both return values and both are dependent upon each other. Notice that the foo passes x and then calls bar with the value b. Then b, which is actually defined in foo, is passed to the parameter y. So y becomes b. So 3 into b. So say b is 5. If x was 0, b 1. So b is 5. So 5 into 3 stored inside a, and that is printed also. And then the value of a is returned by bar here, and then it is returned again here inside C, and then it is printed out. And this is how it looks inside a simple stack diagram. You see the stack bottom return address to return from main to invoke main. So this is the part that operating system handles. Don't worry about what invoke main is right now. Again, as I said, there's a lot when dealing at the low level. You don't want to overload yourself, don't go into tangents. We will study the tangents when the time is right. Okay, here we see return address to to return from foo to main. So from foo to main, how will you go back? So inside the main frame you will have a return address, and that is right also, right? From foo to main, so foo to storing data into main. Return address to return from bar to foo. Okay, so inside the foo frame we are returning from bar to foo. Okay, clearly visible. Then inside the bar frame we are returning to nobody, right? We're just returning a value and that is being used by foo. If there was a bas or a alpha beta gamma function after this, then yeah, we'll be returning to that. This is the top of the stack and that is the bottom of the stack. Okay. So what happens when you add a single local variable and try to decompile that program? Exactly what happens is on your screen. We have a int function, int I equals to 5, scalable. This is a cool way of writing scalable. And you see return I. So we are returning the value of I, and then we are returning the value of I again through main. So if you write this, the code that comes in is so and so. Now I understand this code is not properly aligned because some changes were made to the image later on, which have made it look like so. But no issues. So here you see RSP 18. So you are subtracting 18 hexadecimal from RSP. You will see this a lot, especially when you're storing, integer variables. You will usually see this. You'll see a D word or a double word pointer to RSP's address, and this value being stored in that address. So move is basically copying this value right here, storing it at the address that is in the stack pointer right now. Okay. And because the stack pointer was decreased or pushed down, if you remember from yesterday's class, when you push down, what happens? When you push down, what happens? The stack, you get more empty space, you get some new data space of the undefined space in the RAM, where you can actually store your values. So you're actually trying to create space by subtracting, then you're moving and storing, then you're moving RSP pointer into EAX because you have to return the exact same value. Realize that you have to return I only, and I is what? This. And I is just a label at the high level, right? So what is I at the low level? Just the address of RSP. So whatever stored at the address that is stored inside the RSP is your return value. So you take that, you put it in the EAX, and then you simply add 18 to the RSP back, and then you simply run the function code and you return a new exit. So what you are realizing is that this is not very well optimized code. You could optimize it further because I is being used for basically everything. So you could just have like 3 lines of assembly code and you can optimize this further. And the compiler can actually do that. The compiler can actually manage to do this. It is just that this is not optimized code. So now let's talk a little bit about functions with single local variables. Here, this is how the disassembly looks like. Again, I'm not going to waste too much time, so you can pause the screen because now you know the logic. So please pause the screen, just have a look. You can also write the code, download IDA freeware or Binary Ninja Trial or a few other interesting tools that I'll tell you about in just a second, and decompile the program yourself and disassemble it yourself and just have a look. Okay, you can also use object dump that I showed you in Linux in the last class. So that's another option that you have. Linux has Redare 2, which is pronounced Redare, and let me show you the tool. So it's Redare 2. I think that's, if I can spell properly, then yeah. So this is the tool, Redare 2. This is a fantastic tool in active development. As you can see, 6 hours ago was updated, and this should provide you with more than enough features, to just quickly let you reverse engineer your binary. They have a Python library as well. They have, graphical interface. They have the normal Redare software. And to be honest with you, Redare is just a fantastic, overall toolkit that will let you, extract and do a lot of things, as you can clearly see here. Just a fantastic tool, used by a lot of hackers, especially top CTF players in the world. You'll see them using this. A lot of bug bounty and malware researchers use Redare. Redare is a fantastic tool. You can also use Pwn GDB. So you can just type Pwn GDB, and this is another one of those tools that is known to be extremely fantastic, easy to use, and very powerful. There's also another plugin for GDB called uh, GDB. I'll show. I'll show you guys a nice script actually to install a lot of the different plugins um, that I came across my research. Again, all the credit goes to Andreas. So let me open this up. There you go. This is the script. Highly recommended. Installs Speda, installs PwnGDB and GDB check. All three. It's a fantastic script. Works on most Linux distributions. I have tested it on. So I've tested it on Debian and Ubuntu based systems such as Kali Linux, Parrot. I've used it on Arch Linux multiple times. I've used it on Gentoo, and I've also used it on Linux from scratch. So it basically works on everything. It was recently updated this year only, so it shouldn't have any issues. This is all configuration background configuration file creation thingy script, so it shouldn't break anything. It should be pretty simple, and I highly recommend that you go ahead and use the script and just restart your terminal in Linux, and you will have access to all these extensions for GDB. Again, all the credit goes to the author. Fantastic guy, does great work. So with that, I think a rough idea is there about the different utilities and tools you can use to reverse engineer and get the disassembly, and to write your own code and then disassemble it. And this is one of the easiest ways to learn. You can just write your own code, disassemble it yourself, and try to understand what each and every line of what you have written does. Sounds simple, but as you start writing if else statements and for loops, you start to realize that there's a lot of clever tricks that no book teaches you. You have to really, compiler design is a black magic. Okay, like even in universities, it's not really taught how the most modern of compilers and commercial and enterprise compilers and you know enterprise JVMs and God knows what else works. They don't talk about the internals, and many times there's just so many things about how something works that is hidden from you. So to learn it, even if it's proprietary, all you have to do is just disassemble it. And here is when I want to introduce a notion to you, and the notion is very simple. The notion is that nothing in this world is closed source software. Listen to me again. Nothing in this world is closed source software. There may be proprietary software and non-proprietary software, but there is no such thing as closed source. Why? Because every piece of software, no matter how well coded, how well obfuscated, all that becomes useless in the face of assembly language and machine code. When you disassemble something and you break it down at that level, all that becomes useless. So technically, you could just take any proprietary software out there, that any old game or whatever, and you could reverse engineer it A to Z, and you could understand every single code the coders have ever written. Now, there's a legal gray area here for a lot of programs. If you do this, it's fine for education and research, but if you're trying to use it commercially or tell other people, it usually becomes illegal. But as far as I have done my legal research, it's okay to reverse engineer if it's for your knowledge sakes and it's happening on your local system. If you're teaching it to somebody else, showing it, publicizing it, and it's commercial software still being used a lot, then it may be illegal. Okay, I would like to point that legal nitbit out because a lot of people have made this mistake before me, so I'm not going to make that one. Let's just clear the air right there. So this is how a simple structure looks written inside C, inside assembly language. Again, not gonna waste too much time here. I'm expecting the viewers of this course to know C language because C is kind of a prerequisite to get into low level. So if by now you still don't know C or you have trouble with C, I highly recommend going on YouTube and searching for C courses, and you will find hundreds of courses, 14-hour, 17-hour, 21-hour courses, proper university courses that providing formal education in C and C theory. Please go through C once again, especially the advanced topics such as structures. This is really going to help you, and then come back, write your own structure, and then keep it very small and basic in the beginning and decompile it and see how it looks, and then come back to this video, pause exactly here, and look at the decompilation here. Okay, I understand that the lining is not done properly. I know I'm triggering the OCD of a lot of people. I apologize beforehand. The image is completely my fault. I take responsibility for it. So the process of creating an assembly language program means that the right of assemble, when you press enter, line will crunch up the result and print it to you. Assembly language is not structured in the same way as C, Java, Pascal is constructed. Very pointedly, you cannot write assembly language programs by trial and error, nor can you do it by letting other people do your thinking for you. So assembly has to be your thinking. Every single line of assembly has complex logic behind it. Just cannot go like if and then think for 10 minutes. No, not how it works. It is complicated and tricky process compared to something like Basic or Perl or even Ruby or any such visual environments such as Delphi, Lazarus, and Gambus. You have to pay attention. I am an old guy, okay? Yeah, Delphi. I have written that. For those who know what I'm talking about, they know. You have to read the sheet music. Okay, what and what's inside them. So a file is a collection of data stored on a medium of some kind. I repeat, a file is a collection of data stored on a medium of some kind. It is nothing more, nothing less. It is just some collection of data. And what is data? Stream of binary numbers. Always go back to your basics. Okay, what is a file? A file is a collection of data stored on a medium of some kind, maybe a hard disk or SSD. What is data? Stream of bytes. That's how computer understands and handles data. What are these byte numbers and how are they saved? There's probably billions of switches that are being flipped to create these binary patterns. So you have to always come back to basics in assembly to truly break down every concept. The collection of data is given a name and manipulated as a unit. So hence a file. Okay. Now, when you're dealing in the Linux and the BSD world, there is a concept here that I want to go into. So let me exit out and type everything is a file. This is the concept. It's a very infamous concept, and it's really popular. It basically describes one of the defining features of Unix and its derivatives, that a wide range of input output resources such as documents, directories, hard drives, modem, keyboard, printers, even some inter-process and network communications are nothing but simple streams of bytes. I repeat, are nothing but simple streams of bytes exposed through the file system namespace. What is file system namespace? A collection of data given a name and manipulated as a unit. So in Linux and BSD world, everything is a file. Basically, that is Unix philosophy. So anything based out of Unix is having that concept, and everything is treated as a file. Windows treats files a little differently. Okay, it has a Windows registry and there's some complex machinery behind. So Windows is a little bit more complex, but if you're trying to understand a file properly, Linux and BSD is the way to go. So what is a binary file? It is a file which contains values which do not display meaningful as text. That is a simple definition, right? A binary file is something that runs on your computer. It's probably closer to what a computer would understand compared to what you would. So that makes sense. It's a binary package. Is an application that contains pre-built executables built from source code and are not reversible. This is wrong. I do not agree with this sentence. This is a famous sentence said by Dr. Yuka's Hemio. This is something I do not agree with. Binary packages can clearly be reverse engineered, as we've been saying. It's art, it's a science, it's a skill. It takes time, but even if it takes you 20 years, you can reverse engineer any piece of software in this world. Okay, that is the first thing I want to instill in all of you. The most important advantage of a binary is the ability to hide source code and prevent future modifications. Again, this is also wrong. You can patch a binary also. All that knowledge is actually part of our PGDCD, Post Graduation Diploma in Cyber Defense. So we'll show you how to patch a binary as well, how to go in, play around with the bytes, and inflate and deflate the package and do so many more interesting things with it. Binary files contain machine code and can be executed on the system. Yes, this is also a clear feature. All the data encoded in binary files cannot be readable by humans. These files store anything except text. Again, not completely true, especially with ELF files. You will see a lot of strings being stored, so there is still some human readable text that can be extracted. Okay. Now you might be thinking, hey, what is this guy? His own PPT he's contradicting. Yes, I am. That's one of the reasons I wrote it down. These sentences sound logical, but when you try to understand what's going behind the scenes, you realize, okay, they may not be true so much after all. What's the then what are text files? So text files are basically files that can open and be examined meaningfully in a text editor such as Notepad in Windows, or any many text editors that are available in Linux. My favorite being Vim and Vim. If you thought I was going to say Emacs, no. I hate Emacs. I'm a Vim guy. It contains uppercase, lowercase, numeric digits, punctuation. It also contains a group of characters called white spaces. Again, Unicode, white spaces, ASCII. Not good touching that right now. We'll go into that sometime around day 4, just for a little bit. It is easy to display, edit, and understand. A text file is used to store standard and structural textual information, or information that is human readable. Okay, so I agree with this slide more or less completely. So how do we interpret raw data? Seeing a text file as a line of hexadecimal values is a very good lesson in a fundamental principle of computing, that everything is made of bits and bit patterns. What we mean is that what we agree that they mean. The capital letter S that begins both of the two text files displayed in Bless is the hexadecimal number 53. So what you have to understand is that, so Bless is, by the way, is a very old editor in Linux. Okay, no matter what you see in text, it's actually being shown to you in hexadecimal, in a hexadecimal editor. So even in IDA you must have seen there was a hex view, so you could see the text in hexadecimal. That is where the advantage comes to your benefit. You should actually start looking at binaries with a lot of text and text files with a lot of text inside a hexadecimal editor, something like hexedit in Windows. Okay, and on Linux there's like 100 different ways to look at the hexadecimal values. What going to happen is that you're going to start learning the patterns of what 53H hexadecimal is, what 12H is, what AH is. So you have to learn. It takes time, okay, to recognize hexadecimal patterns. Rest of the text, please just go through it. I'm gonna go ahead because again this is not very important for our current discussion. We need to talk a little bit about NDNS. So NDNS basically means that uh, differences in display order versus differences in evaluation order. So I'll come to the evaluation order in just a sec. First, let me discuss NDNS. So um, here I think this should, yeah, this example should help you understand. NDNS basically means how values are interpreted by your CPU. Don't look at the complex diagram. Listen to my voice. Close your eyes. Listen to my voice. NDNS means how your CPU, how your alien overlord computer looks at a value. If it looks at in a straight form, it is big Indian. If it looks at it in a reverse form, it's little Indian. Understood? No confusion? That's it. Don't worry about the offsets. Move on. I'll come back to this. What an assembler does. Yeah, okay, so this is basically what an assembler does. You have an assembly instruction such as move ESP to EBP, and it converts it into this hexadecimal code, EBH. Okay, this is pure hexadecimal code. Some comments to note here about what comments are, and how we usually write them in languages such as C. They also exist in assembly, by the way. Comments do exist in assembly. Please pause and read through the theoretical part here about what a EOL marker is, if you wish to do so. Now the assembler and the linker. Let's spend 5 minutes here. The assembler is basically what assembles your code, and the linker links it with the libraries that you are using. So program code including named procedures, references to named procedures lying outside the module, named data objects such as numbers and strings with predefined values, named data objects that are just empty space and set aside for program use later, references to data objects lying outside the module. So here you can see multiple .asm files or assembly files, source code files, put into the assemblers to create object code binary files. These are still somewhat human readable. And by the way, the ASM files or the source code files are just text files. Okay, this is just raw text, human readable stuff. binary files in object code is somewhat human readable. When you link it with all the libraries, you get a single executable program file called myprog or my program, which is very less human readable unless you go into assembly language and disassemble it and break it line by line. Only then it is readable. Otherwise, human readability is less. Again, theory. I am not going to explain reload cryptability property here. This is all theory of linker and compiler design. I felt it was useful because it's taught in college education. So if you're doing specializations in compiler design, you'll probably be learning all these concepts. So please just read through this. And you can ask questions again in the chat box or in the live chat as well if you're watching it live, and you can communicate with me. I'll be more than happy to answer all your questions and try to solve as many problems and confusions as possible. And if there's any big questions, I might actually add those to next day session, those questions answers, so that you and others can be helped in going forward with this learning journey. Okay. Again, most of this you already know, so not wasting too much time here. We are using the NASM assembler, which is the net-wide assembler. So please just pause and read through if you wish to. Please note here that debuggers are an extremely crucial piece of tool that we have in our toolkit as hackers. I'll be coming back to this. So please just read through this to understand the theory behind this. Practical, you leave it to me. I'm not much of a theory guy. You tell me to rip apart a binary, I can do that. So we'll be going into GDB soon. I'll be showing you some demos with GDB as well. So you'll see the step into and step off logic as well soon. So you edit the program in editor, step 1. You assemble the program with NASM. So you write the program, then you assemble the program. This is the general process of how we assemble an ELF binary on Linux with the assembly language file or .asm source code file. Okay. We link the program using the LD command like so. Please pause if you wish to read this, and let me quickly pause a few seconds for those who want to pause and have a look at this as well. There we go. Now I'll pause here for a few seconds. And then we test the executable file. We try to test it out. And testing is a very important part of software development that a lot of people forget, especially when you're in college or you just joined a startup or you're launching your own startup. You might want to just make an app and just put it in production. Testing is extremely important. So please try to test, okay? Watch it run in a debugger. Again, debugger will be coming into the debugger section soon. Thank you so much for joining me for day 2 of Zero to Hero in Assembly Language CERT-In session for the language of Cyber Defender taught by Cybervidyapeeth Foundation. We wish to see you there again for day 3. Please go back, do some study, watch the video again if need be, do your own research, and try your best to understand the intricacies of low-level programming and deep systems engineering. I would like to point out again that the postgraduate diploma in cyber defense admission is still going on because there was a confusion due to the image being shared here by me that it ended in 31st October. No, it hasn't. The admission is still open. Please feel free to join in with us in a journey to master cyber defense in a 1-year intensive course also known as Cyber Rakshak Advanced, taught by us at Cybervidyapeeth Foundation, backed by Vinoba Bhave University, Hazaribagh, and the government of Jharkhand, as well as University Grants Commission of India. It will be a full-fledged degree diploma, and it will be 12 months in total, including a 200-hour plus Israeli simulator access. So you will be allowed to practically test every single theoretical concept that we'll be teaching. We'll also be teaching you how to create your own home labs and how to play around with technologies such as Active Directory and malware analysis. We wish to see you all there. Please scan the below QR codes for more details, or please mail us at mentor@cybervidyapeeth.in for more information regarding the course. Thank you so much for joining us for day 2. I wish to see you all there for day 3. It's been a it's been a blessing working all with all of you. I got a call from a lot of students yesterday, and I'm sure a lot of you are eager to call me today and ask questions. I'll feel free to answer all your questions. Please note my handle is at stupid pineapples on Telegram. So that's my username on Telegram. You can just text me on Telegram that way. Feel free to hit me up, ask me questions in my free time. I love to you know get in with the community and answer your questions about reverse engineering, malware analysis, and all the other related topics. So feel free to join us. We love to see you here for a lot of our other courses. If you really are interested in making a career in in your cyber defense, then please feel free to join our PGDCD, or at least contact us about it. We'll be more than helpful to we'll be more than happy to help you with it. And hope to see you again soon. Dhanyavad. Jai Hind.